So, welcome everyone, people in Zoom and in the room. So it's a great pleasure to have Davide Ruffoni here in Strasbourg, and we know each other since our PhD. Davide got his PhD at the Max Planck of Colloidal Interfaces in the Department of Biomaterials. And you work mainly on simulations, on no experiment, and it was more on bones material. Then it was postdoc in Zurich at ETH, and he started to do some experiment, and some experiment that we have already here. We have also here the tomography, X-ray tomography, and investigate several materials. And then he got a professor position in Liège, where he has his own group and still work on Bioinspired or biological material, combining both simulation and experiment in his group. So we are very happy to have you here. The floor is yours, David.
Yeah. Can I take off the mask? Ah, okay, thanks. Thank you. Thank you very much, Antonio, for the nice introduction. And thank you very much, you all, for being here, and also for people that are online. I'm actually very happy that I'm here to present the research that we are doing. That's my first seminar after turbulent years. So it's nice to be here to do this. Just one couple of pictures actually to show you where I come from, or where I'm working. Actually, I'm Italian, as Antonio, but I work in Liège, which is a city located pretty much in the middle of Belgium, in the French part of Belgium. And actually, before moving to Liège, the only thing that I knew about Liège is this famous bike race, Liège-Bastogne-Liège. But then I discovered that there are other nice things in Liège. There are very nice, tasty beers, a bit strong, but very tasty, as chocolate also. And then there is also university, which is giving me, work. The nice thing about the University of Liège is that it's the only university in the French-speaking community of Belgium, which has a university hospital. And there is especially if you are in my field, in biomechanics, biological materials, there is a strong connection with medical doctors. So we have a strong collaboration with the doctors there. And last but not least, in Liège, there is also my group. So it's a group of very, let's say, motivated PhD students. And the research that I present is mainly done by Laura Zorzetto, who is now working at the Max Planck Institute in Potsdam, where both Antonio and me did the PhD. So as Antonio said, I'm interested. I have two research lines, somehow complementary research lines. I'm interested in biological materials, and especially I'm interested in the interfaces between different types of biological materials. So the main focus is on materials of the musculoskeletal system, and those interfaces which connects different materials of the musculoskeletal system are very interesting because they have to solve a very challenging task. So they have to connect two tissues, like, for example, tendon and bone, which have a very dissimilar mechanical behavior. So not only they have a very different, let's say, stiffness or Young modulus. Bone is very stiff, is about 20 gigapascal. Tendon is more compliant, about 0.5, 1 gigapascal. But they have also very different deformation mechanism, energy absorption. And these two tissues are connected over a very, do I have to stay in some location? No? Are connected over a very small length scale, which is about 500 micrometers. And there is a special dedicated area to connect those tissues, which is called enthesis. And this is very, let's say, relevant also clinically, because there are many pathologies. And when those when this enthesis breaks, for example, due to sport injuries, we are not able to reconnect these as in the, let's say, healthy scenario. So we are trying to learn what is happening here and how to, let's say, also translate these into synthetic materials to facilitate the attachment of very dissimilar man-made materials. So in parallel, what we are looking at is bioinspired materials. So what I mean by that, I mean that we are investigating biological materials, and we focus on selected construction principles at different length scales. And then we try to reproduce these and to translate these into synthetic materials. And this will be the main topic of my presentation of today, which I will enter now in more details. So as a motivation, why we are doing this, actually, I like to motivate by showing you these two mechanical properties, which are here on the x-axis, the Young modulus. So the Young modulus, as you all know, describe a little bit so the resistance of a material to a deformation. So a material which has a high Young modulus is a material which needs a high force to be deformed, like ceramics, for example. And on the y-axis here, I put fracture toughness. So fracture toughness is a little bit a more complicated property, and we can describe it as the energy that you need to put in a material to break it. And why do we plot these two properties together? Because normally they are in contrast. So a material which is very stiff, it's normally very brittle, and the material which is very tough is normally more compliant. And so in nature, if we take the example of bone, bone is composed of a mineral, calcium phosphate, which is a ceramic-like material. It's very stiff, but also very brittle, and is composed of proteins, collagen, which are polymeric materials, so to say, biopolymers, which are soft, but also very tough. And bone has the ability to combine these two and to make the best of the two properties. So when we, let's say, combine the two, we have a tissue, or we have a material, a biological material, which is both stiff and tough. And in classical engineering materials, although they have higher properties than biological materials, just the relative combination of those properties is not as efficient as what nature is doing. So when we combine those properties, we always have a compromise which is not there in biological material. And the question, this is a little bit why we consider this as a nice source of inspiration, and we try to replicate those features in engineering materials by trying to see which are the tricks that nature is using in those biological materials, such that they can combine these conflicting properties. And the idea is that we focus on what we call architectured materials. So what we all know is that biological materials have virtually all biological materials have a hierarchical structure. This is an example of wood, for example. So an example of wood has a hierarchical structure ranging from the nanometer level, where you have the basic building blocks, the elementary building blocks, up to length scales of centimeter or of meter, where you have the full organ or tissue or component size. And by architecture materials, so architecture materials are those materials where we can define well-defined structural arrangement or structural motifs which are intermediate between the elementary building blocks, which, as I said, are typically at the nanoscale, and component size at the centimeter or meter level. So we are interested in developing bioinspired materials where we can control architecture at multiple length scales between our elementary building blocks, which I will show you what they are in case of our bioinspired materials, and the overall object size. And of course, one advantage of introducing an architecture inside the material with respect to a monolithic homogeneous material is once again represented here in terms of mechanical properties. So I will focus mainly on mechanical properties, but there are other aspects which are also interesting in architecture materials. For example, the ability to introduce multifunctionalities. But in the talk here, I will consider mechanical properties. So if you consider homogeneous monolithic material, typically those materials are quite stiff, but also very brittle, and shows, let's say, a sudden or more catastrophic failure. And when you insert an architecture, so when you play a little bit with the arrangement of the basic constituents, you can obtain, or you can program the behavior of the material such that the material you can delay the failure, and you can somehow improve the energy absorption capability of the material. And this is where we are playing a little bit with these type of concepts. So there are two different aspects that we are considering to introduce an architecture in a material. So one traditional aspect is to use cellular solids. So cellular solids are porous material where we can control the pores, or complementary, we can control how we place the material, the arrangement of the material, and we can tune the mechanical properties, for example. So they combine typically what we know from engineering. Cellular solid materials combine lightweight and also extensive and easy, if you want, tuning of mechanical behavior. And this can be done without changing chemical composition, of course. And another construction principle that we see very often in biological material is that they are composed of fibers over many length scale. I'll come back to this in a second. They are composed of fibers over many length scales. Fibers are typically biopolymers, which are reinforced by different strategies with mineral crystal, for example, or with covalent crosslinks. And fibers in biological materials shows a very rich book of different structural motifs, ranging from unidirectional fibers, helical fibers, combination of multi-layers with fibers oriented in different directions, or also the so-called Bulligan architecture, where planes of fibers are stacked on the top of each other with different angles, and they provide extremely high fracture resistance properties. And so these construction principles are very often seen in biological materials. Typical example here, once again, is bone, which I investigated a lot during my PhD. This is an example of a vertebral human bone, so from the spine. And what you see when you zoom in is that bone is indeed a highly porous material. So it's a lot of volume inside our bone is empty, and you find bone marrow there, so which has no mechanical role. But what is taking the load, which is let's say transmitted across vertebra, are those small structures which have a length of about 1 millimeter, which are called trabeculae. So these are, let's say, stiff beam elements which are arranged in different ways to take up the load of our bones. And when you zoom in even more here inside this structure at the micrometer length scale, you see that one trabecula is actually not a homogeneous material, but is composed of fibers. These are so-called mineralized collagen fibrils, which are, let's say, arranged in bundles, and also these have different directions depending on the position where you are in the bone and on the loading requirement. So constructing a material with fibers allow a highly versatility. It also allows to have superior failure resistance, for example, crack resistance, crack deflection, and provides multifunctionality. And so these are now the construction principle that we try to replicate a little bit in the synthetic materials using 3D printing. So actually the aims of the research that I'm presenting is really to prototype architecture materials which are inspired by biological composites using three-dimensional multimaterial printing. So the idea is that we start from an observation of a construction principle of a biological material. We focused a lot on bone and on wood. And then we isolate the construction principle, which is typically at a small length scale, as I said, intermediate between nanometer and millimeters. And then we scale this up. We, let's say, simplify this, and we decide which features we want to replicate. We use three-dimensional printing. And at the end, we use experiment computer simulation to understand if these construction principles is also working in artificial materials, and to see a little bit the constraints and the advantages that is bringing to the Bioinspired structure. So that's a little bit the research principle that we are following, or research strategy that we are following. So what I will present today is a very short introduction to this type of multimaterial printing that we're using. Then I focus a little bit on the interfaces between the different materials. Since this is a multimaterial approach, one issue is that there are interfaces between the different materials, which have been not a lot investigated. And then I show you one example of a Bioinspired helicoidal composite material, and then of a cellular solid material that we have been developing. So the first thing that I want to speak about is this three-dimensional printing. So we are using a commercial printer, and I will tell you a little bit later why we choose to go in this direction. So the printer is a polymer printer. is based on the deposition of monomers, liquid monomers, droplets of liquid monomers, which are then flattened by a roller and cured by UV light. I think there is even a small animation. Yes, so there is the printer head is moving from left to right, is depositing different droplets of different polymers. They are deposited on the build tray, they are flattened down by a roller and then cured by UV light. And typical, let's say, droplet dimension are about 20 micrometer, and layer thickness, this is of course a layer by layer technique, and layer thickness is about 20 micrometers. So that's the resolution, the theoretical resolution of the printer. And what is nice is that with this printer, you can combine different basic polymers, so liquid inks, which in this animation are only 2, but now the new printers are able to, they work with up to 5 different inks. And so different inks then results in polymers, cured polymers with very different mechanical properties. And they are, yes, so let me just say this and then I explain you about the mechanical properties. So this technology is called polyjet printing, is based on photocurable monomers. Since it's commercially, is a commercial printer, is stable, is reliable, but of course is a proprietary technology, so there is no possibility yet to customize the inks, for example, inserting like nanoparticles and so on. This is something which is not really easy to do. That's probably the technique, the multimaterial technique commercially available, which has the highest resolution, because we have droplets of about 20 micrometer, from 20 to 40 micrometers in diameter, depending on the layer. And this allows them to build objects which are about 25 centimeter in size. So we have this control over multiple length scales. And then is, as I said, multimaterial. And the 2 basic materials, so the 2 most extreme materials that we can use are the stiffest materials, has a Young modulus of about 2.5 gigapascal, so it's hard plastic with an elongation at break of 15%. And the softest materials is it has a Young modulus of about 1 megapascal with an elongation at break of 220%, so it's an elastomer. So we have 3 orders of magnitude variation in mechanical behavior that we can combine. So in that sense, it's multi-material, although it's still based on polymers, but we can cover a spectrum of 3 orders of magnitude. And what I find very interesting is that we can fabricate so-called voxelated soft hard matter. So I repeat a little bit myself, we can build centimeter-sized objects which have a programmable composition and structure at the micrometer level. And there is a nice Nature paper from the group of Jennifer Lewis at this institute that describe these, let's say, the new avenues which are opening on this type of voxelated materials. Now, okay, this was the short introduction. And now I focus a little bit on the interfaces between different voxels and different materials in this technique. So, yes, let me just, this is what I just said. We can tune with this approach, we can tune local microstructure, chemical composition, mechanical properties. We have 2 different droplets which are deposited and which are then cured on this layer. And the question is, what is happening at the interface between these 2 different droplets or these 2 different polymers, depending a little bit on the printing modality. And if you enter in the details of the printing process, there are 2 different ways that 2 polymers can get in contact. So you can have a simultaneous deposition of the two polymer, which are represented here with the 2 colors. So they are deposited simultaneously. So they get in contact on the build tray before being cured by UV light. Or they can be deposited consecutively. So you can first deposit one polymer and then cure. And then on the top of an almost fully cured polymer, you deposit the second droplet here, and then you cure this. So this is something that we call that the interface is formed after curing, and here the interface is formed before curing of the 2 polymers. And we are asking a little bit, what are the properties of the interfaces in these 2 different scenarios? So yes, the two aims of this research is to characterize the size of the interface between these glassy and rubbery polymers. And for that, we use, since we have a micrometer length scale droplets, we have to use a technique which allows to have this resolution. And so we choose to use nano-indentation. And then we want to assess the mechanical behavior of the interface and the impact of having an interface which is not ideal, so it's not a zero thickness interface, which is the impact of this interface on the behavior of multi-layer composites, simple multi-layer composites. And for that, we use dynamic mechanical analysis and some numerical modeling. Yes, so I think here I can go a little bit quicker. We prepare the samples first for nano-indentation. So we printed small samples where the interface was formed before UV curing. And by changing the orientation of the samples, we obtain samples with interface formed after UV curing. And then the problem of nano-indentation, what we need to have a very smooth surface, which is also a little bit tricky in case you have polymers with such big differences mechanical behavior, because you cannot do standard polishing from metallurgy. So what we did here, we did a cryomicroton cutting. And so we had a very smooth surface, nanometer scale roughness, and then we could nano-indent. So we pressed a diamond tip on the samples and measure a little bit the force and the displacement of this tip. And then we used models to, based on force displacement curve, to get the local Young modulus, basically. And this is also a little bit tricky, not straightforward, because we have to indent in stiff polymer and in soft polymers. And in soft polymers, you have adhesion effect. And this is something that you have to take into account when you indent in this. So I think here I don't enter too much in the indentation procedure, but maybe I just show you the differences. These are typically load displacement curve when you indent in a hard material. So this is not surprising. This is quite well established. There are established equations to then derived, let's say, from the unloading stiffness, from fitting this curve, you can derive the reduced Young modulus, the Young modulus of the material. Problem is that when you indent in the soft material, you have very different behavior. So you have, when you're, let's say, you are approaching the surface of the material, you have a jump into contact that you see because of the tip is approaching the surface, and then you are indenting, and then you have large adhesion forces that you see by this negative peak here, if you want. And so this then changes a little bit the procedure and the way you have to fit the data. Yes? Yes, yes, this is something that, so, yes. I should have not showed that picture. It's okay. No, it's okay. So this is, there is some pores in the soft materials, but I don't think those are caused by the pores. I think these are also caused by the cryosectioning. But the problem is that we didn't see these everywhere. So they seems to be localized close to the interface. So when we indented, we made sure also to try to avoid these as much as possible. But we also indented in those blisters, and we didn't see big differences in terms of behavior. So we said, okay, we are still. There is another picture where I think it's less dramatic, the presence of those. Yeah, but it's a good point. So yes, and so we need to indent a little bit, develop. Fortunately, there is already quite some literature also in this indentation of very soft materials, so we could exploit this a little bit, and basically from our measurement we could estimate the contact radius between the probe and the sample and use this to derive the so-called reduced modulus of the indentation. And now I jump to the result. So these are the properties of the interface that is formed after UV curing. So one polymer is deposited on the top of an already partially cured polymer. And what you see here, going from the stiff to the soft polymer, this is relative position, special coordinates, and you see that there is a very sharp transition of about less than 20 micrometer. You have a transition between your 2 gigapascal and less than 1 megapascal in properties. And here what we have, so here you see that we don't see those blisters anymore, not these regular blisters anymore. This is now we indented between stiff, soft, stiff, just to acquire a little bit more point to see the trend of the interface. And you see that the interface is much broader. and we measure an interface, let's say, thickness of about 150 micrometers, which is several times the dimension of the droplets which are depositing. So there is some diffusion, and there is let's say, also some mechanical diffusion, if you want, because of the roller, which is a leveling of the layers, plus some probably chemical diffusion, if I could say, mechanical and chemical diffusion. I don't know if I can say that, but in any case, there is some other chemical diffusion, which also the droplets, the monomers, the oligomers, let's say, they interdiffuse in the droplets and they are broadening the interface. So these are a first, let's say, results that we have obtained to show how critical the thickness of the interface depends on the printing modality. And then we wanted to assess a little bit the impact of the interface on the behavior of very simple multi-layer composite materials. So we, let's say, printed composite materials at the millimeter length scales of alternating layer of soft and hard polymers. And we printed them such that the interface between the different layers was sharp or was very broad. So we printed these, and then we performed dynamic mechanical analysis to measure the dynamic properties. So dynamic mechanical analysis, we basically use a 3-point bending configuration, and we scan the behavior in different temperature ranges to get what is happening also across the phase transitions. And the main, let's say, output that we consider is the so-called loss modulus, and the tangent delta, which are typical parameters to describe the dynamic behavior of those polymeric systems. Now I will just show you this. So this is basically a plot of the storage modulus. Let's concentrate in this region around room temperature and a little bit away from glass transitions. And what is happening when we increase the number of layers? So this is a system of where we have only 2 layers, stiff and soft. This we have 4 layers, 6 layers, and 8 layers. So the volume fraction of the stiff and soft phase is always the same. We are simply just redistributing this across the cross section of the system. So this changes the area moment, and this changing the bending behavior. And what we see if we have a so-called blurred interface, so the 150 micrometer interface, is that when we increase the layer from 2 to 8, the storage modulus increases. And this is not surprising. This is also in agreement with composite beam theory. So simply because you are redistributing the stiff material across the interface, you get a bit more rigid behavior. Okay, this is something that is predictable, understandable, and we were happy. The problem is that if you do this now with the sharp interface, so it's exactly the same configuration. Layers are distributed from 2 to 4 to 6 to 8, but now the interface between layers is very sharp. So there's basically less than 20 micrometer. In the other case, it was 150 micrometer at least. And then we see that there is no changes. There are no changes in the mechanical properties when we increase the number of layers. So everything is flat. It stays from 2 to 8 is the same. And we said, okay, but this is also something that we see here in the full, let's say, storage modulus versus temperature curves. These are, I didn't say that this is in gray is the storage modulus of the stiff phase, and in black of the soft phase. And this is the storage modulus of the different layers. And here, once again, I zoom in a temperature range a little bit away from the transitions. Now, this is something that we didn't understand at the beginning. And so what we did, this is also in contrast with the beam model. A simple beam model would predict an increase in bending rigidity because we are redistributing the material. But what we see is that the bending rigidity does not depend on the number of layers. So I said, okay, what is going on? So to understand this, we did some finite element simulations. So we translate our system in a virtual material. We did finite element analysis, replicating the experimental conditions, and we consider sharp interface or blurred interface. And what we see is that in the case of a sharp interface, indeed, also in our simulation show no increase in bending rigidity by increasing the number of layers. So these are simulations with blurred interface, which were the same, let's say, qualitatively similar to the experiments, and those are simulation of sharp interface, which are also qualitatively similar with experiments. What is happening actually is that in the simulations, what we accounted for are shear behavior. So when you have a very sharp interface, let's say there is a transmission of stresses which induce a lot of shear in the soft layer. And so the layers, let's say the stiff layers they deform, there are a lot of shear deformation between the stiff layer induced by the soft layer, which are not present when there is a blurred interface. So this is just a little bit a didactic example to show the impact of such interfaces, even in very simple geometrical arrangement like this multi-layer composite. And then what we did, we went a little bit further, and we also tested we designed other samples. So this is an optical picture of the interface between the rigid and the compliant polymers. And we tested now the samples in tension, not in 3-point bending, but in tension, still dynamic mechanical analysis, but in a tensile configuration, because in a tensile configuration, we could use a simple rule of mixture model to get a little bit the properties, the dynamic properties of the interface itself, which is not possible if the system is in 3-point bending, because it gets a little bit too complicated, especially for the loss properties. So we could then use a simple rule of mixture and come up with a model to predict the storage modulus, the loss modulus, and the tan delta of this. And then we compared a little bit what is happening in these simple plate-like multi-layer samples when we have different amount of interfaces due to different amount of layers. And so what we see, actually, to make a little bit the story, to cut a little bit the story, to make it shorter a little bit, what we see is that the interfaces, although you are mixing, let's say, equal amount of polymers, soft and hard, is strongly dominated by the rigid component. So the interface has properties which are strongly dominated by the rigid polymers, and also in the interface itself, the viscoelastic dissipation, which are typical of the soft polymer, are totally suppressed. So that was a little bit surprising. And yes, I think this I can skip. So in conclusion, here we have proof that there is a formation of an interface of this 3D printing multimaterial approach, which can be several times bigger than droplet size. And then this blurred interface is actually an interface. So it's a third material, which has properties which are more similar to the glassy polymer, both, let's say, storage properties and loss properties. No, sorry, storage, yes, yeah, storage properties and dissipation properties. And we have shown that the performance of these simple multi-layer 3D printed composites are critically dependent on the interface. And these, of course, can provide new design criteria for multi-layer materials where we have to account for the presence of the interface. So I go maybe to the second study, and then I take questions at the end, if it's okay. Then I show you now a study that we did on helicoidal composites, that now that we know a little bit what is happening with the interface, we know which dimension we expect to the interface. I want to show you a different study where we introduce now fibers. So the idea, the motivation is that many biological materials, as I said, are constructed with fibers, and fibers have also some typical helicoidal arrangement. And two examples are bone. So bone is composed of two types of bone: cortical bone, which is a very compact type of bone, and trabecular bone. Trabecular bone I quickly presented before when I said in the vertebral body we have a highly porous type of bone. This is trabecular bone, which is here. And cortical bone is very compact, so we have a very small porosity inside cortical bone, but there is some porosities, and these porosities are there because we have a blood vessels. So in bone we had blood vessels to bring nutrient to cells, and these blood vessels are somehow protected by features which are called osteons. And osteons are cylindrical features where we have fibers of collagen which are arranged in an helicoidal fashion. So this is something at the micrometer length scale. This is something that we see in bone. And in wood, is similarly, we have also helicoidal arrangement. Where do we have helicoidal arrangement? We have this in the wood cell wall. So a tree is composed by wood cells, and the wood cell wall are the stiff part which are taking up the load of a tree. They are composed mainly of cellulose, hemicellulose, and lignin. And cellulose forms fibers which are also helically, spirally arranged in the cell wall. Now, what we know is that the cell wall in wood is composed of many layers, and the most important is also multi-layer material. The most important are these S1, S2, and S3 layers. These are concentric layers. S2 is occupies about 80% of the thickness of the wood cell wall, and S1 and S3 only the remaining part, 10% and 3–4% respectively. Now, we know that S2 layer, the one which is the thickest, which occupies 80% of the thickness, is composed of cellulose microfibril, which are spirally wounded around the wood cell wall. So this is a single wood cell, which is an elongated cylindrical structure. And these are cellulose, so it's a stiff crystalline polymer composed of sugar-like molecule, let's say, which form characteristic angles. And we can measure these angles with X-ray diffraction. And what we know is that this angle is used, let's say, by nature to tune locally the mechanical properties of the wood material without changing chemical composition. So if you have angles which are very small, you have vertical fibers, and you are in a situation where your wood is very stiff, but it's also very brittle. So the fracture strain is very small. And when you increase this angle, you decrease the stiffness, the Young modulus, but you increase the fracture strain. So the wood cell wall behaves like a spring. And this is done by tuning the angle of these, let's say, molecules. And our idea is somehow to, let's say, translate this, which is quite straightforward, let's say, in artificial materials with 3D printing. And then we want to exploit, which is a little bit less straightforward. We want to understand the interplay between a central layer with thick fiber and inner and outer, or let's say outer and inner reinforcing layer with much smaller fibrils, and to see which is the mechanical interplay when I try to reinforce a central layer where fibers have some angle, and when I try to reinforce these with smaller fibers, either internally or externally arranged. And this is something that is not so clear, and also in wood is not so clear which is the role of S1 and S3 layer. That's why we said, okay, if we do this, we could maybe learn also a little bit why in wood we have also these much thinner layers where fibers have typically horizontal orientation. So they're not well-defined orientation as in this central layer. So what we did now, we designed, we had to scale this up because of the printer resolution. So we cannot print this at the nanometer length scale of cellulose, of course. So we scaled this up at the millimeter length scale. And we printed the system where we have a central layer, and which is representing 60% of the thickness of these cylinders. And these central layers is then reinforced by smaller layer, S1 and S3, which are about 20% of the total thickness of the system. And in terms of fibers volume fraction, the central layers has a volume fraction of 30% of fibers, the rest is a soft matrix. And we have a 3 to 6% volume fraction of reinforcing fibers in these inner and outer layers. And so we combine now different configurations. So we had the main layer with fibers which are 0 degree vertical up to 45 degrees. And as reinforcing layer, we consider both only horizontal and vertical fibers. So we try to reduce a little bit the parameter space and to see the interplay in terms of mechanical properties when we play with these structures. How much time do I have? Still 5 minutes approximately, right? 15 in total? Okay, thanks. So we 3D printed this, and we consider actually stiff fibers. So the fibers that we inserted are about 2.5 gigapascal, and we consider 2 types of matrix such that the elastic contrast between fibers and matrix is a factor of 500 or more than a factor of 1000. So what we call soft matrix of ultra soft matrix. So the matrix is an elastomeric matrix, and the fibers are glassy rigid polymers. And then we performed some mechanical tests to failure, and we explore a little bit the behavior of the system. So one first question we had was, which is the minimal dimension of the fibers that we can print? So we did a preliminary study to see a little bit based on the resolution of the printer, of the interface dimension, what we could print. And we came up with the minimal diameter to see fibrils, which are still, let's say, representative in terms of mechanical behavior that we want to insert, is about 750 micrometer. And then we scale it up fibers to 3 millimeters. So our, let's say, fibers here have a diameter of 3 millimeters, and they have reinforced with something that we call fibrils, so smaller fibers with diameter of 750 micrometers, so a factor of 3 less, up to a factor of 3 less. And then what we did, we first did a little bit an analysis of the stiffness, the apparent stiffness of the system by changing the fiber winding angle and also the maximum compressive strength. So we see that we can indeed, this technique allows to, let's say, tune or program the stiffness of the system. And also we had similar trend, qualitatively speaking, for soft and ultra soft matrix. Maybe I will quickly skip this because I want to show you this, which is most interesting. Then I come back to this. Then we performed experimental test to failure. And what we see is the following. So this is the behavior for the situation of straight fibers. So we have a cylinder with straight vertical fibers. So this is not a big surprise. When we compress this system is buckling. So it's going into buckling failure. And if we add either vertical reinforcement or horizontal reinforcement, well, we don't change too much the behavior. So we have a small increase in the buckling strength, but the behavior is substantially the same. And this, we are not tuning so much. We are not influencing and reinforcing the structure. What is interesting is that what is happening when we do the same exercise, but now the main fibers have some angle. And here I present the result of 15 degrees, for example. At 15 degrees angle, well, we have a system which, first of all, does not show a big failure, or let's say catastrophic failure, as the straight fibers. And what is interesting is what is happening when we add, for example, vertical reinforcement. Now you see we are reinforcing the tilted fibers with some vertical fibrils. Well, they provide a little bit an increase in stiffness, but essentially the behavior does not change a lot. What you see here is this collective buckling or kinking of these vertical fibers, which are, let's say, is a collective buckling because they somehow feel each other through the matrix. So as soon as one fiber is buckling, all the structure is buckling. But what is interesting is now when we, oops, didn't I have another picture? Yes, when we introduce the horizontal reinforcement. So the horizontal reinforcement now on this structure are able to delay the failure and to increase dramatically the strength of the system. And this we see also if we explore or if we examine the post-failure structures. And in the case of vertical reinforcement, we see a long crack running through the system. And in the case of horizontal reinforcement, we see that the crack at some point also runs diagonal. So we are also tuning the way it breaks. And because of this, we have 100% increase in failure stress, 50% increase in failure strain, and we have a structure which absorbs 150% more energy. What we also did, I wanted to show maybe this plot here. We ran some finite element simulation of the same structure to understand a little bit how the structure is deforming. And what we saw is that if we introduce, for example, the horizontal fibers, what we are blocking is the expansion of those cylinders. So when we compress and we measure the Poisson ratio, so the expansion perpendicular to the direction of compression, we saw that with vertical fibers, we are pretty much similar behavior as with no fibers, and with horizontal fibers, we are blocking the expansion. We have a much smaller Poisson ratio. And on the other side, what is increasing the rotation of the cylinder. So this is something, the rotation along the vertical axis is increased where we add horizontal reinforcement. So the horizontal reinforcement are actually more triggering more rotation of the system, and this is something that is delaying the failure and also is deviating the crack from vertical to horizontal direction. So I think this is something that we, let's say, showed this. To conclude this part, we performed those, let's say, study to assess a little bit the role of these reinforcements that is inspired by the structure of a wood cell wall. We developed samples which show similar trend as our simulations. We prove how the reinforcements are avoiding this catastrophic failure. And what we have that just a minimal increase in volume fraction, if we place the fibrils in a smart way, let's say, this allows to delay failure, and we could obtain a little bit of programmable mechanical behavior. Now I show you the last study, which is more on cellular solids construction principle. And what we are interested in here, this is not too much bioinspired, because this is something that we don't see very often in nature, but an interesting type of structure which got a little bit our attention are so-called auxetic structure. Auxetic structure are structure which shows a negative Poisson ratio. And the negative Poisson ratio, as you know, is that if I have a non-auxetic material and I apply tensile force, this material shrinks in the direction opposite to the tensile force, and an auxetic material expand in the direction opposite to your tensile force. Right? This shows this auxetic behavior, and the same is true for compression. Non-auxetic material, let's say, expand in the direction perpendicular to your compression, and the auxetic material shrinks in this direction. Now, why are those materials interesting? Well, there are several applications that one could think about those for those materials. One application is that it is known that they show enhanced impact resistance, because in a non-auxetic material, when you have, let's say, a local indentation, let's say, the material have the tendency to flow away from the indentation point. And in an auxetic material, the material has the tendency to concentrate in the indentation point. And so this is then reinforcing, let's say, the impact, or sustaining more the impact, let's say. And they also show a very non-trivial deformation mechanism. So typically you have an anticlastic curvature for non-auxetic material which are bent, and the synclastic curvature for auxetic material which are bent. So they show also deformation modes which are non-trivial. And one of the most used way at the, let's say, millimeter length scales to produce auxetic materials is through cellular solids. So you can tune the microarchitecture of the material such that your structure shows auxetic behavior. And why we are interested on those materials? Because we thought, okay, there are some theoretical prediction that if you combine materials which shows as, let's say, positive and negative stiffness, and you combine them in a composite, you could have some, let's say, enhancement of mechanical properties. So this was assumed theoretically, but was never, let's say, demonstrated. And then we said, okay, but maybe we could use cellular solid principles, design lattices that shows combination of reentrant, auxetic inclusion, non-auxetic inclusion, and see a little bit which type of behavior we can have. So we combine so-called hexagonal lattices that shows classical, positive Poisson ratio behavior with reentrant lattices, which shows these quite simple lattices, which shows this auxetic behavior. And then we said, okay, what does it happen when we combine those two? And the idea is first to study the effect of a, let's say, single auxetic inclusion in a otherwise regular lattice, to see if the auxetic behavior is retained when I place the inclusion and I take it out from a auxetic lattice and I place this in a regular lattice. Does this retain the auxetic behavior or not? And then what does it happen if I make a pattern of inclusion, and what is the overall behavior of those structures? So first of all, we introduce this auxetic phase just by shifting one, we call this one joint. When the connection between three beams is one joint, we shift it down, and then we have an auxetic inclusion. The lattice is otherwise very big, and we then simulated, when we compress this, what is happening at the level of this inclusion. This was a little bit the research question. So we apply a uniform compression, and we compare the behavior with respect to a regular lattice. So we could, with the simulations, we could get the deformation in each point. So we consider these triangular, let's say, unit cells, which are the basic unit cell that you can repeat in space to build up your hexagonal lattice. And by knowing the, let's say, the displacement in each of these vertices of this unit cell, we could calculate the overall strain of the unit cell when is inside the regular lattice. Well, if it's inside the regular lattice, the strain is everywhere the same. This is isotropic material, is an isotropic structure. And the question is, what is happening when we have an auxetic inclusion here? And what we saw is the following. So if we compress this along the vertical direction, and here I plot the strain of the unit cell with respect to the strain of the regular lattice. So in the regular lattice, when I isolate one single unit cell, its strain with respect to the strain that is in a regular lattice is 1 because it's regular, so everything is the same. But if I consider the unit cell, the auxetic inclusion, I see that its strain is less with respect to the strain of the corresponding regular lattice locally. And so this means that it's deforming less, so it's a little bit more resistant, right? When I look at the vertical direction, is the direction that I compress. So the lower deformation at the reference unit cell is locally stiffer. And when I look at the strain in a horizontal direction, so I compress it vertically and I look at the strain in the transverse direction, and I see once again that in the regular lattice, this is 1 because it's isotropic. It is yes, and this means that this is a Poisson ratio close to 1, right? Is the ratio between the two. And here I see that is negative. So this means that this auxetic inclusion, although is placed in a otherwise regular lattice, can still retain the auxetic behavior. So although the environment around this inclusion is not a completely reentrant lattice, but now this is like, you have to see this as a defect inside the regular lattice, but it's still able to carry its own character, let's say. And so we said, okay, but now since this is stiffer, it has this auxetic behavior, let's now try to generate a pattern of inclusion where we introduce not just one as before, but we introduce several reentrant inclusion. And we could introduce up to 12.5 volume fraction of the entrant inclusion and what is happening in terms of apparent properties. And our assumption is that this lattice is more stiff because the inclusion, they have a contrast deformation mode. The regular unit cell, they want to expand, the other wants to contract, and this creates some contrast in the deformation mode, which is then stiffening the lattice. So we did both simulation and experiments, and we see that indeed the apparent stiffness, so in the stress strain curve and the tangent modulus here, which tell us the apparent stiffness, is actually indeed higher for the lattice with the pattern of auxetic inclusion. And this is up to 300% increase in stiffness without changing the relative density. So what I find nice is that we don't put more material. We are not changing the anisotropy. We are not orienting this differently. The anisotropy stays the same, or the isotropy, let's say, stays the same. The relative density stays the same, but because of this contrast in the formation mode, we increase the stiffness up to 300%. And yes, I think this is now the conclusion. I have 2 more slides. Do I have time for those 2 slides? So this is now to conclude, is now I show you, let's say, what we are doing in terms of our research in 3-dimensional printing, a little bit this influence of printing parameter on the interface. Then I show you how we design and print helicoidal composite inspired by the structure of wood, and also some cellular solid composite which exploit this reentrant auxetic, non-auxetic behavior. And a little bit 2 slides of outlook, what we are doing now. We are interested again at interfaces, but now we are interested at tuning the interfaces to enhance the attachment between the similar materials. So I come back a little bit of what I said at the beginning. And in nature, we see 2 main strategies to attach the similar materials. One strategy is what we see in the muscle that has to attach to a solid rock. And we see that this attachment is through these long polymeric bundles or threads, which displays gradient at the level of centimeters. So those filaments are graded in composition and in properties at the level of centimeters, several, or let's say several millimeters up to centimeters. On the other side, on the opposite side, there is the attachment of tendons to bone, musculoskeletal system, whereas here the, let's say, the gradient is on a much smaller length scale, which is only about 500 micrometers. So these are two different strategies where we are trying to somehow explore and replicate in the attachment of the similar engineering materials. So in this example here, we are trying to, let's say, engineer the interface between a hard material and a soft material, which will be here. Just the frame around is just printed because when we need to cut with the cryomicrotome. But now let's only consider this direction that we are going, let's say, from a very hard material to a very soft material. And we do this by depositing, let's say, hard or soft voxel. And by changing the spatial arrangement of those voxel, we are trying to understand how are the elastic properties changing across the interface and how can we, let's say, program different spatial configuration of soft to hard voxels such that the interface shows increase in failure resistance. So this is something that we are doing more at the length scale of several millimeters. And at the smaller length scale of, let's say, only some tens or let's say hundreds of micrometers, what we are doing, we are introducing, instead of a large perturbation of a large gradient, a long gradient, we are introducing very small perturbation. So we just perturb the interface between a rigid material and a soft material only by changing 4 voxels. And so what this is defined as a minimal surface patterning or interface patterning. And we, let's say, introduce different designs, different patterns between soft and hard voxel and to see the corresponding failure behavior. So these are 2 different things that we are exploring. And we see that here, for example, just by changing only 4 voxel up to 300 voxel in length, this system will be 300 voxel in length. We change only 4 voxel. Each voxel has a dimension of about 400 micrometers. And what we see is that we, just by changing these 4 voxel with respect to a flat interface, we have an increase of more than, let's say, yes, 30% or so in the failure strength of the system. And this is something that we are currently, let's say, working on. Now I just would like to thank my co-authors. So we have collaboration with Politecnico di Milano for the characterization of the interfaces, with ANSYS for the mechanical simulation. We have a partnership, and also colleagues in Berlin and in Delft for this 3D printing, voxel 3D printing, FNRS, which is the founding. And thank you all for your attention.